Hello and welcome back to Calculus 2, Chapter 11 on power series. So we talked about sequences, which was ordered list of numbers. And then we talked about series, which was sum of the sequence. So let's write those in. Sequence is an ordered list of numbers, and we had the AN as its notation. Series is the sum of the sequence, and we had summation AN, and we only considered infinite one because the finite one always converges. Finite has finite amount of terms. When you add them all up, you get a value, and that's it. So now the goal for us is to discover power series. Now, power series is going to have an independent variable x in it. So power series is a series with independent variable x. They look like this. Summation, let's say 0 to infinity of Cn x to the n. And it is technically an infinite polynomial. So it's C0 plus C1x plus C2x squared plus C3x cubed plus ... forever. And I'm just going to say infinite polynomial. Polynomial must have the end term, must have, right? You know, because that's how you define a polynomial. What's a quadratic polynomial? Well, the one that has x squared in it, right? And then a cubic is the one with the x cubed. But if I don't know where the last term is, it's technically not a polynomial. So this thing is we call it infinite polynomial because it doesn't have the highest term. It goes to infinity. So there is going to be x to 73 million, and there's going to be x to 1 billion, and x to, right? And it's going to go forever and ever and ever. Now, this particular polynomial here is what we call centered at 0. Yeah, see, I'm allergic to one of the guys who walked in.
Must be him.
I don't know. So we want to actually center this at any value. So the formula that we all want to know is Cnx minus a to the n. And then that's going to be C0 plus C1x minus a plus C2x minus a squared plus C3x minus a cubed plus going on to infinity, and I'm going to put that one in a cloud because that's the one centered at A. Power series centered at x equals A. We will understand eventually why is that so important. Now I would just like to see what would one of these look like. So starts at 1, let's say, or 0, doesn't matter, start at 0, whatever. Let's have a summation example, just to see what it looks like. Let's start at 0, go to infinity, have maybe 2n, and then x minus 3 to the n. That's an example. Let's put it up there, right? So this works out to be an infinite polynomial. When n is equal to 0, it kills everything because it will be 2 times 0 times something to the 0 is 1. So it will be 2 times 0 times 1. So first term is 0 plus. And now when n is equal to 1, we get 2 times x minus 3 when plus. Next term is n equals to 2. That's going to be 4 times x minus 3 squared plus when n is equal to 3 is going to be 6 times x minus 3 cubed plus dot dot dot. So this is called power series, and this Cn is called the coefficient. So this puppy over here, I'm going to point purple into it. That's the coefficient. And it's centered at A. So the bottom one is centered at 3. Now we'll understand what that means. Right now it's just mechanics of coming up with these things. I would like you to try and say summation 0 to infinity. Did I mention that 0 factorial is equal to 1 before? When I talked about factorials at the beginning of 10-7 root n ratio? Did I mention that by any chance? Okay, that's something that you would not know unless I say it. So please go back in your notes to 10.7. Write in 0 factorial equals 1. It's a big deal when we start working on these power series, and if you don't know that, then all hell breaks loose quickly. 0 factorial equals 1, because I want to put the factorial now. And so n factorial times x plus 1 to the n. And I want you to write out terms, at least 4 or 5 terms for this problem. I hope you have about 4 or 5 terms worked out. And we're going to say 0 factorial x plus 1 to the 0 plus 1 factorial x plus 1 to the 1 plus 2 factorial x plus 1 squared plus 3 factorial x plus 1 cubed, and let's do 4 factorial x plus 1 to the 4th plus dot dot dot. You have to use the dot dot dot. So now 0 factorial is 1, x plus 1 to the 0 is 1, so the first term is 1. plus x plus 1 to the 1 plus 2 times x plus 1 squared plus 3 factorial is 6 x plus 1 cubed. 3 factorial is 1 times 2 times 3, right? So that's 6. And then plus 24, because now it's 3 factorial times 4, which is 6 times 4, 24, x plus 1 to the 4th, plus dot, 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 going forever. And there is no sense in expanding these things and adding them together, because dot, 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 there is the 1 to the 5th and to the 6th, right? So wasting time to simplify this much is a waste of time, right? Because you're not going to get to the highest degree, right? Now, what are these things? These are series, definitely, right? You have your n and the summation, but they also have x. And because they have x, they can be used, hold your chairs now, to transfer any function into a polynomial. Do you know what that means for integration and derivatives?
So much work.
It erases all of your calculus completely up to this point. If you know how to differentiate or integrate a polynomial, everything else that we learned so far completely useless, right? Power series, all right? So we're going to see a lot of cool stuff. Now we have to build up to that point. So there is a lot of things that we need to know. Derivatives are used, obviously, and all of these kind of things. We'll see what it means. But just the fact that you can turn a function into a polynomial, and then you probably already seen, if you took physics and your teacher ever said, for small angles, you replace sine x with x. Like, really? Sine x and x are nothing apart. But he also said, for small angles. We're going to understand that today. And that's why I have Desmos ready to do some graphs and for us to understand why is this thing so damn important and why it drives your electrical engineering 100%. Right? This. And you're going to have chapter 3 differential equations to be solving differential equations using these puppies. Remember shifting the counter? It's going to kick in. Oh, we'll see. Okay. So now, what do I want to do with this? Why is this thing so important? So here is something that's called Taylor series. And Taylor series are just one of the power series. Guys, there are Taylor series, there are Fourier series, there are Lorentz series. Depending on which course, on which level of math education you are, you're going to learn a whole bunch of different series. Taylor series are polynomial-based series. Fourier series will be trig-based series for periodic functions. And then you are going to have Lorentz series in a complex domain, and so on. So there are going to be different types of series for different levels of math. Some of them might be 400 level undergrad, and some of them definitely graduate school, right? So you are not done with mathematics by learning the first one, right? Which is today Taylor series. Now this thing has summation Cn x minus a to the n from 0 to infinity. And now we have a formula that computes coefficients Cn. So Cn is going to be f to the n at a divided by n factorial. So this is, I'm not sure which page is this on.
On page 711.
711, 709, 710, somewhere in here, 711. Good. All right. So Taylor series, Taylor polynomial are given by this. Both of these, so I'm going to put the comma there, and I'm going to put this into a cloud. And this might be as well the most important thing you learned in all of calculus. All right? So now, what is this thing? Well, if you consider what I said, that it turns any function into a polynomial, then it might be something very, very powerful. So this is what I'm going to do. I'm going to develop Taylor polynomial. I'll put in parentheses series for sine x. Those of you that didn't see this notation before, you should have seen it in Calc 1. I'm going to poke arrow here and say nth derivative. Zeroth derivative is the original function, and we generally use prime, double prime. You can use triple prime, but you're not going to use 4 primes and 6 primes and then go 7 tick marks for 7th, right? We start placing numbers inside the parenthesis. Usually 4th derivative and 5th and 6th, right? So we use primes for the 1st, 2nd, and 3rd derivative. Those little primes. But when you hit the 4th derivative and on, we put 4 in parentheses, 5 and 6 and 7 and so on. All right, cool. In order for me to create the power series, the Taylor polynomial, for sine x centered at 0, x equals 0, that just means a is 0 for our calculations, because it's x equals a, and then a, right, is where the 0 is, so a is 0. So develop Taylor polynomial, Taylor series, for sine x centered at x equals 0. I don't want to overwhelm you with all of the things, but in the book it's clearly stated when you have a equals 0, it's called Maclaurin series. It's a special case. So everything is called Taylor series, just like you have linear functions, a special polynomial, quadratic function, special polynomial, cubic function. Those are all polynomials. It's just special ones for, because they're used a lot. So if you center something around 0, it's called Maclaurin series. But Maclaurin is just that one case. If you center it around any other number, it's just called Taylor series. So we might as well call everything Taylor series, including that one, because it's just one simple. And I don't think that's mentioned until all the way into 11.3. So I wouldn't even bother, but that's okay. All right, are you ready to be blown away? Lock the doors. We are going to take a whole bunch of derivatives of sine x because we are going to need them.
Well,
so,
before you do that, I just have a question.
Yes.
The f to the n where you said it's the nth derivative.
That's what we're going to do now, yep.
That's not an exponent?
It's not an exponent, it's the order of the derivative. Okay. That's why there are parentheses around it.
Okay.
So when there is no parentheses, it's the exponent. When you put the parentheses, it's the derivative. That's the notation. Good question. So, but you were going to see it now in notation here. Okay. F prime is cosine x. F double prime for the second derivative is negative sine x. F triple prime, 3 of these guys, is negative cosine x. And then f, and here is the switch in notation to the numbers. We have sine x. And then here's the 5th derivative, cosine x. And I'm just going to put 3 dots because the thing is going to go forever. So when you are transferring your function into a Taylor polynomial, you have to find a whole bunch of derivatives first. Okay? Now that you have that, you are going to write out your Taylor polynomial. We can do it here on the side. Summation Cn x minus a to the n from 0 to infinity is going to be equal to the summation 0 to infinity of f to the n computed at a divided by n factorial and then x minus a to the n. So that is us plugging in the coefficient formula. It was used to be separate. And finally now, we are going to write out f to the nth derivative of 0 divided by n factorial times x minus 0 to the n. I can just say x to the n. I don't need to write 0. It's just x to the n, because a is 0. Let me write it in blood. Equal to 0. There we go. For this problem, it could be 3, it could be 7, right? In this case, I clearly stated I want it centered at 0, so that's why a is 0. All right, cool. This is my formula that I'm going to plug the stuff in. So what's my first term when n is equal to 0? So when n is equal to 0, I just have the 0th derivative is the original function. So I have f of 0 divided by 0 factorial times x to the 0 plus the next term is the first derivative divided by 1 factorial times x to the first power plus second derivative computed at 0 divided by 2 factorial x squared. Guys, this is a pattern. Everything is 0. Everything is 1. Everything is 2. Third derivative computed at 0 divided by 3 factorial times x cubed plus fourth derivative computed at 0 divided by 4 factorial x to the fourth plus the last term that we took the derivative for. There are infinitely many terms. 5 factorial x to the 5 plus dot dot dot. You must have dot dot dot. So this is n equals to 1, n equals to 2. Maybe I should have these in purple. N equals to 3, n equals to 4, n equals to 5. You're just plugging these things in. And now it's time to compute. What is this equal to? Well, the original problem is sine. So I have sine of 0 divided by 1 times 1 plus first derivative is cosine, so that's a cosine of 0 divided by 1 factorial is 1 times x plus derivative of cosine, which is the second derivative, was negative sine of 0 divided by 2 factorial is 2 x squared plus the third derivative was negative cosine of 0 divided by 3 factorial is 6 x cubed plus the fourth derivative was sine again, so sine of 0 divided by 4 factorial is 24 times x to the fourth plus the fifth derivative is cosine of 0 divided by 120 x to the 5 plus, and I'll put 3 dots. You have what these derivatives are. You did them all, right? So you know what the derivatives are that you are supposed to plug in for the derivative part of the formula. Except when you are moving from one to the next, you have to move from one to the next on the list of derivatives. And now you just compute all of these. Sine of 0 is 0, so first term is 0, plus cosine of 0 is 1, so this one works out to be x. The next one is sine of 0 is 0. 0 divided by 2 is 0 times, so that's 0 also. Next one is the minus 1 over 6x cubed. Then we have sine of 0 is 0, so that's a 0. Then we have plus 1 over 120 times x to the 5 plus dot, dot, dot. When you get rid of all of the zeros, you get x minus x cubed over 6 plus x to the 5 over 120 plus dot, dot, dot. This calculation claims that you can replace sine x with this polynomial. Now, I'm just gonna, dig into my head over here, and I'm going to write that sine x can be replaced by x minus x cubed over 6 plus x to the 5 over 120 minus x to the 7 over whatever the hell 7 factorial is plus x to the 9 x9 factorial minus, and I'll put the 3 dots. I just added a whole bunch of terms because I know them.
It's 5040 for 7 factorial.
Something like that, yeah. So I'm going to actually switch now these two into 3 factorial and 5 factorial. And you would go, huh? You can write a polynomial instead of the trig function? Well, let's do some graphing, right? Let's do some graphing and figure some things out. Figure out what happened in that physics class when they said you can replace x instead of sine x. That made no sense whatsoever, right? Just x is a linear line, right? It's 45-degree linear line. How can that replace the wavy sine function? All right, so here we go into Desmos. And the first thing I'm going to graph, obviously, is sine of x, which is this wavy red line. You see all of the features. It goes through 0. Trying to see that, okay, there we go. You see a full period. Do we see how it's negative 6 and 0.28 and positive 6.28 for 2 pi on each side? So are we all green on that? Great. Now, what did the formula say? What did your teacher say in physics? Just graph x. Okay, there's your x. Do we see that the blue and the red line are on top of each other around 0? Oh, that's what it means, centered at 0. Ah, okay, now I understand. Because if it was centered at let's say 2, then the blue line would be around 2, matching the red line, right? So that's what a centered means. We'll have much more on that as we go along. Okay, so now what we did in class is we added extra terms. So we have x minus x cubed divided by 6. Oh.
Yeah, that's not need to press forward.
Yep. Divided by 6. Ooh. Look at the green line. Do you see that the green line is following the red line a little bit longer than the blue line? What do you think is going to happen when I take this function and add the next term? Another squiggle is going to pop up and follow the red line even more. The more terms you put in, the more it's going to bend around the function and eventually bail. Polynomial is not periodic function, right? Polynomial is not a periodic function. So polynomial can never do what sine does forever. But we don't care. We care for small angles, right? To calculate stuff in a first quadrant, and that's it. The rest of engineering we don't care. So I'm going to add now plus x to the 5 divided by 5 factorial, which is 120. And you can see now this dark blue, follows the red line even more. So now when I make this much larger for you guys to see the just one side, for instance, a red line is your original sine. Then you have the light blue line, which bails quickly, right? So maybe, pi over 6 or pi over 4 on each side for the blue line. Green line goes maybe all the way to pi over 3. They are matched. And look at the first 3 terms. Covers the whole first quadrant, right? 90 degrees. You keep adding extra terms, it keeps wrapping around. Keep going and going and going and going. So I'm just going to add the other 2 terms that I mentioned. So it's going to be copy. I'm going to subtract x to the 7th divided by 7 factorial. And then we're going to add another x to the 9 divided by 9 factorial. That's this black line. And look at the black line following the red line. Almost to 2 pi. I effectively turned the sine function into a polynomial. And you can just imagine what happens. Remember how you have to memorize the sine squared? You had it on your exam. There was the double angle formula, the power reducing formula, and then you can't integrate. Well, how about you just write it as this and square these values and integrate that? It's like, really? Right? So that's the idea of power series. So what we are learning here is to turn the function into a power series and then deal with polynomial all the time in terms of limits, derivatives, and integrals, and that's your 11.4, right? The calculus of power series to apply instead of limit of sine and derivative of sine and integral of sine to just do those 3 of the polynomial. And we know that that's the easiest. Now, obviously, polynomials have their bad, evil side, which are called roots, right? Finding roots of polynomials is a living nightmare, right? Unless it's just a basic quadratic or something, then it's easy. But having anything more than a quadratic, it's just kill me now, right? But in terms of calculus, polynomials are woohoo, right? They're awesome. Polynomials are awesome. So hopefully now you understand why is this done by looking at this graph, and we can go and see what other cool properties we can figure out. Now, can anyone tell me something interesting that you learned about sine function back in pre-calc that you were just told, just remember it, and then eventually you'll know why? What kind of function is sine function?
Oh, it's an odd function.
It's an odd function. And you have to use the brain power, right, to know it's the odd function, because we told you memorize that the sine is odd function. Why is it odd function? Look at the exponents. They're all odd.
Oh my god.
What's going to be for a cosine?
It's gonna be 0, 2,
Even.
4, 6.
Yes, they're going to be all even powers. And that's why they're all even and odd. I mean, sure, the symmetry works and everything works mathematically for even and odd in a trig form, but it is insanely cool. It is insanely cool. And you know how the derivative of sine is cosine? You just take derivative of each one of these terms and it gives you...
Oh my god.
It clicks, guys. It clicks like this. You have no idea. The entire chapter is one lecture. I have to work hard to separate all of these things because I'm not supposed to tell you all the way until 11.4 that if you differentiate each one of these, you will get exactly what the series is for the cosine if you did all of this mess from the beginning for the cosine. Okay? So if you go and you start f of x is cosine and you take 5 derivatives and you go through all of the same steps, you're going to come up with 1 plus x squared over 2 factorial minus, right? You're going to get that. 1 minus x squared plus x to the 4 minus x to the 6. And if you take the derivatives of each one of these, they fall exactly into that.
And then it divides against the factorial. It just corrects the factorial.
Yes, because these 3 would drop down, right?
And then divide it out.
And divide into this and make it into factorial 2. Yeah. It's math. It just clicks. So now we actually have a list of power series somewhere in this book that are going to tell you power series for this, power series, blah, 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 right? So now I would like to challenge you for like 10 seconds to come up for the, we call this Taylor expansion for e to the x about 0. So come up with a Taylor expansion. That means do the same steps we used for sine. Get 5 derivatives of e to the x. That's going to be tough. And then just plug everything in. E to the x is bad, first example. All right, so same steps like for a sine, get 5 derivatives. So you will end up with 6 terms, right? The first term you always use the original function. So if you take 5 derivatives of e to the x, you're going to end up with 6 terms, the expansion. let's take a look at this problem together. The function that I would like to represent with the Taylor polynomial, which means do the Taylor expansion, is e to the x. So f of x is e to the x. Now, the first derivative is e to the x, and all derivatives are e to the x. Cool. So the Taylor polynomial, or the Taylor series, or the Taylor expansion, use any of the three you want, is going to be summation, what's going on over here? 0 to infinity of the derivatives calculated at 0 because I am centering it at 0. Next one we're going to center somewhere else. Divided by n factorial times x to the n because it's x to the a 0, so blah, right? All right, so let's go. We start with 0th term, which is original function, so that's going to be e to the 0 divided by 0 factorial x to the 0 plus. They're all e to the 0. All of these derivatives will be e to the 0 because we have it centered at a is 0, and this value here is value a if you look at the formula. So all of these are going to be e to the 0. 1 factorial x to the first power. I don't want that to be a prime. Then e to the 0 divided by 2 factorial x squared plus e to the 0 over 3 factorial x to the 3 plus e0 over 4 factorial x to the 4th plus dot dot dot. This works out to be 1 plus x plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot dot dot. And what you learn from here is that e is not even, not odd, because it has both powers represented. And now we can go quickly to Desmos and take a look at this polynomial following the e to the x function. So now we're going to jump back to Desmos, kill all of these, and start from scratch. E to the x, and when you do that, you get your basic red. Now let's do first three terms. 1 plus x plus x squared divided by 2. Do we see how around 0 you have the blue line match the red line? And now in the next one, I'm going to quickly cut and paste. So copy, paste, plus x cubed divided by 3 factorial. And let's do one more term. X to the 4th divided by 4 factorial. And that's your green. You can't even see the red. We did 5 terms, right? So, cool, right? Now we have a polynomial instead of e to the x. The new feature that I'm going to introduce with this problem is compressing this into a series, into a summation, right? So if we look at this, right? So this is my answer. This is the polynomial. You can go with x cubed divided by 6 and x to the 4 divided by 24, but that's my polynomial. Now, what I'm going to do is to condense into summation. And the way we do that, and this is important for your differential equations, if you are going to differential equations, we are going to write this as x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial. I hope you see immediately how to push this into a single series, right? What is it? Summation, 0 to infinity, and what should I write?
X to the n over n factorial.
X to the n over n factorial equals e to the x. So next time someone tells you, what do you know? E to the x is equal to summation x to the n over n factorial. What do you know?
Thanksgiving stuff.
Yes, 2 weeks. You can lead with this problem. You know. Start with, oh, by the way, did you know? And then just write it out. It's going to be... You have so much good material in Calc2, right? Learn it at least for the memes. Like, if nothing else, just learn it for the memes. Now let's go and expand away from 0, right? Expand around 3, expand around 7, or whatever else, right? So what should we expand? How about we expand? Let's expand ln of x plus 1 about 2. So your f of x is ln x plus 1, and now you're going to take, let's go with three derivatives, 4 derivatives. Let's do 4 derivatives. Come up with 4 derivatives and then start plugging stuff in. The creek.
You know what? I'm gonna start writing one because this is like the third time somebody asked me and I feel bad.
Why would you feel bad? That's what I don't get.
Because like I'm pretty useless anyway. And it's
What do you
like,
mean you're useless? You're
Oh,
not
you
useless.
don't even have a stapler.
You're not useless. What do you mean useless? Relax.
Thank you. Can I ask a question? Because I don't want to do the whole thing if it's wrong. Does it become ln x minus 2?
So you first calculate ln the derivatives, right? So you have 1 over x plus 1, and then and then you will plug in 2 for each one of those x's, because you'll have them all in terms of a, and a is 2. So you will compute all of these for 2, and then you will use those. So let's take a look. The first derivative over here is 1 over x plus 1, yes. So that's our first derivative there. Copy the function as is and then do that. And then we have the next derivative, which is take the derivative and it should be, we have x plus 1 squared, like that, right? And the derivative of the inside is still 1. But it's a negative 1. So now it's going to be positive 2 over x plus 1 cubed, and then a negative 6 over x plus 1 to the 4th. Are we all matching here? So these are our derivatives. You're just using power rule. You can use the chain rule, the power rule. If you want, you can use quotient, but quotient is, right? So I'll need f of a, which is f of 2, which is ln of 3. Then I'll need f prime of a, which is f prime of 2, which is 1 over 3. I'll need f double prime at a, which is f double prime at 2, which is negative 1 divided by 9. Third derivative at a is the third derivative at 2, which is 3 cubed 27, so 2 over 27. And finally, the fourth derivative, computed at a, is the fourth derivative computed at 2, and that's going to be 81, negative 6 over 81. So these are all my derivatives computed at the value where I am shifting everything. So summation 0 to infinity of my nth derivative computed at 2 divided by n factorial x minus 2 to the n. Maybe you didn't put minus 2, I don't know. Check that out. Let's go. The 0th term, I have ln 3, so ln 3 plus, because ln 3, let's put everything. ln 3 divided by 0 factorial times x minus 2 to the 0, plus the first derivative is 1/3 over 1 factorial times x minus 2 to the 1. Plus the second derivative is negative 1 over 9 divided by 2 factorial x minus 2 squared plus 2 over 27 over 3 factorial x minus 2 cubed, and finally plus negative 6 over 81 over 4 factorial of x minus 2 to the 4th plus dot dot dot. And now we just simplify this as much as possible. And then when I graph this, they're going to match closest in the neighborhood of 2 going outwards. Previous two problems were closest matched at 0 going outwards because those problems were centered at 0. This problem is centered at 2. So when I graph them in Desmos, right, the graph that the ln x plus 1 graph and the polynomial we get out of this mess should match perfectly at 2 and then be close and close and close around 2 and then go away from each other. So we start with ln 3 plus 1/3 x minus 2 minus 1 over 18 when you do the double fraction of x minus 2 squared. Now that's a 9. 81 times 3, 243. So plus 2 over 243 x minus 2 cubed and minus oh no, this was supposed to be a 1 over here, right? Because 27, no, that was wrong. That was 81 as well. That was 81. Because 27 times 3, and then 2 and 2 would cancel. Okay, cool. And now I have, you know what, 6 over 81 times 1 over 2 times 3 times 4. So we'll see what we can cancel. We can cancel a 6 right there. So 3, 2, 4. 3 to 4. Okay, 3 to 4. X minus 2 to the 4th plus dot dot dot. Okay, I got my polynomial. Not pretty to type up, but we can do it. So we'll kill the previous problem. We'll start with our friend ln of x plus 1, close the parenthesis, and bring that one in the view. And then we're going to type up this mess. So we'll start with ln of 3. Can anyone read the rest? Ln of 3 was plus 1/3, right? Of x minus 2. So 1/3 of x minus 2.
Minus 1 over 18.
Now, I want you already to see, oh, by the way, what is the black line?
Tangent line.
Yes! Tangent line. The first two terms are your linearization from Calc 1. You remember that we had the formula, the one formula for the tangent line? It was called L of x. And it had f of a plus f prime of a x minus a. That's exactly your first two terms of the Taylor expansion. And then when you start adding more terms, that tangent line starts bending and following the function. So you see the tangent line, and you guys see that now because it was centered at 2, they are matched at 2. As soon as I add the next term, What was the next term? Plus or minus?
Yeah, minus 1 over 18.
1 over 18.
Times x minus 2 squared.
Look at the back line now bending, and it's still centered at 2. Now, when I add the next term, the black line is going to bend more. You know what? Let's go in the next row. I'm going to keep this calculation here, the black line, and in the next row, we're going to do this. And what's the next term plus?
1 over 81 times x minus 2 cubed.
81 x minus 2 cubed.
Looks like your first term got messed up when you copied it over.
Didn't transfer ln? Oh, ln. Okay, good. Boom, red line. Red line, see, red line is doing better than the black line. So the blue or old purple or whatever the hell that is, that's your original ln of x plus 1. And as you keep adding more terms, this polynomial starts bending and matching more and more and more of your function. What is the key of where you center? That's where they are exactly the same. That's the point of the tangent line. And then the line starts snaking its way right to match the other function. So do we all understand what centered means? So now in 11.3, the distinction is made using names that if you have centered at 0, it's called Maclaurin series. If you have it centered anywhere else, including 0, it's called Taylor series, right? And that's it. Welcome to being about 200 years behind current mathematics while learning that, all right? 1800s, right, when these two guys lived and figured this out. So, yeah, I know, right? So 200. Now I want to introduce you to, a way to be cool in Calc 2. There you go. This is from your textbook. Table of Taylor series. So there they are, all of them, right? And do you want to memorize those?
Wait, you have to memorize them?
No, but you can.
Okay. No, I'll pass, but thanks.
So look, here's your e to the x that we calculated, right? We had this mushed together. There is one for sine. And it's alternating. Is it alternating? Of course it is. Plus, minus, plus, minus, plus. That's alternating, right? Here's your cosine. That was 1 away from the sine, right? Do we see the odd exponent, 2k plus 1? 2k plus 1 factorial for 1, 1, 3, 3, 5, 5, 7, 7. Do we see all even numbers? 2, 2, 4, 4. Do we see 2k, 2k? That's even numbers. Way to write even numbers with these. Now, do you want to jump from sine and cosine into sine and cosine hyperbolic? What is the only thing that is missing? They're the same. There's no alternation. Yeah.
Oh.
Memorizing these guys is a joke, actually, right? Because one would say that you would know these 3 because you did homework. And if you know these 3 because you did homework, then you immediately sine and cosine, you know hyperbolics because you just kick out alternation. So you already know 5, right? Now your intellectual curiosity might ask, this damn e to the x has 1x, x squared, x cubed, but then it has these factorials. Is there a one that just has 1x, x squared, x cubed, which is this one, and that's that, right? And you say, it's a minus. What happens if it's a plus? Just add alternation. Right? There is a pattern to memorizing all of these. We just did this one. And this is technically your e to the x with alternation in it, right? And with one with the minus, you're just going to kill the alternation. Remember your friend tangent inverse? It's on the list. And it's your sine without the factorial, actually. It is so damn easy to memorize the whole chart. The whole chart. But again, not all of you will be working with this. If you're done with your calculus with this semester, you will never see this again. Those of you going to differential equations, this list is your chapter 3. Because you will be solving differential equations by plugging this into the whole thing, shifting the counter and derivatives and all of that kind of stuff, and going from there. Not bad at all. Obviously, really bad if you don't know that e to the x is written that way. So, those of you going to differential equations, you will have to memorize this one, this one, this one, this one, and this one, or you are not going to have fun time in chapter 3, right? So people going to differential equations, those 5 you must know. Anything other than that is a bonus and good, Thanksgiving kind of show off. But those 5 are minimum if you're taking DFQ. And as you can see, as I said, sine and cosine and sine hyperbolic and cosine hyperbolic is the same one. There is a difference of alternation only. Now, how much do you actually have to memorize? Just these 2. Because the derivative of this one is that one, so you just shift each one by 1. You will get that. And then you know that you kill alternation for these 2. So all 4 formulas fall if you know 1. And then e to the x on the side. So that's power series and Taylor series. And the purpose is to take any function and transfer that function into a polynomial. And we saw that even though it's infinite polynomial, right, to set equal between the function and the series, if we use first 3 or 4 terms, it's already good enough for our calculations in engineering, right? Calculations in engineering will also have a safety factor and all of these kind of things to work into it anyway, so we don't have to worry about. And we know that physics is very precise. And your professor still said in class, didn't even bother to put the second term in. For the sufficiently small angles, you can replace sine x with x. Really? Why didn't you say so? Day 1 of math, that I don't have to learn any other functions, just know polynomial. Okay. So this was 11.1 and 11.3. Oh, no, that's it. We're going to do the properties, convergence, and then in 11.2. Okay. Cool. Bye.